All right, thank you for hosting me and having me down here. It's been a really fun couple of days. I've met some really interesting, amazing researchers in all across many departments, which is up my alley. So what I'm going to present today on kind of the big picture of the research that I've been working on for the past 10 years or so, and kind of the future research that I'm planning on working on with a group of students on. So I'll give you some sort of background on why I'm in this area and what I find interesting about it, and the question that drives many of the projects that we're working on. And then I'm going to give 3 examples of research projects that are underway right now with my group. And I won't go too deeply into the methods on these projects, but I'm happy to answer questions. I wasn't exactly sure sort of where people would be coming from, so I'm happy to talk about that at the end. So I've been focused for this part of my second career after the sailing ship career that I had before, working on educational vessels, on maritime systems and seaports in particular. And I'm interested in seaports for these 3 big reasons. They're critical, they're complex, and they're constrained. So they're critical. Seaports are economic engines on the local level. They provide jobs, they provide materials that we need for construction projects, for energy, and they're critical on the global scale. So about 90% of the world's freight moves by ship. So we're a maritime economy. So we really need these seaports in order to make that economy function. And if you think about the things in the room, the tables, the computers, our clothes, they've almost certainly gone through at least 2 ports from where they were manufactured to where they are right now. One on their way out of the country of origin and one on the way in, and likely more than that. They're complex. So ports can be completely private, they can be completely public, and they can pretty much be everything in between, quasi-public agencies. So, and even when you think of a port, we tend to think of the Port Authority. So the Port of Boston, for example, or Port of New York, New Jersey. But ports also include a lot of other businesses that are within their harbor region. So there's lots of stakeholders of ports, from those individual business owners and business managers, the shippers, the tenants of ports, the marine pilots that are escorting vessels in and out, the people who depend on them for their jobs. And there are also many stakeholders across time. So ports are infrastructure, so they last, often many, many decades. And decisions that are made today about infrastructure investments will have implications on future generations. And finally, they're constrained to these very specific locations. Ports need things like deep water, deeper and deeper water as ships get bigger and bigger. They need access to other kinds of infrastructure, road and rail, for example. They need some amount of protection from storm events. And this almost always puts them in estuary areas where rivers meet the sea. And these are also our most critical marine habitats. So ports are located in these areas where we have sensitive habitat and we have hazardous materials passing right across our most sensitive areas. So for all of these reasons, they make a very interesting case study for looking at resilience and climate change issues. And to kind of sum all of this up, what I often say is there's no plan B for ports. So, other kinds of uses on our coasts, if it becomes too expensive, or there's too many storms or there's sea level rise, those uses can be moved. We can move how people can live elsewhere if they need to. But if we're going to have this global economy that we have now, the ports are going to have to be in these vulnerable locations. So without the climate change in the picture at all, ports are already vulnerable. This is a map from a paper that we did a few years ago looking at just the proximity of ports to historic historical tropical storm paths. So this is, the orange is are the historical tropical cyclone paths going back to 1960, and the green dots here are the ports that came within 100 kilometers of those storm tracks. And this represents about a third of the world's ports. So there's around 3,800 kind of major ports in the world, and about a third of them are in the hurricane zones. So even without the climate change impacts, they're already dealing with storm issues and natural hazards issues. What does this mean for these kinds of events mean for ports and port cities? So this is some work that I did, some case study work that I did in Gulfport, Mississippi after Katrina, and then up in Providence, Rhode Island, the Port of Providence. And this work came out of a study that cataloged all of the different kinds of impacts that occurred after a major storm went through a port area. And they broke down into these three broad categories of direct damages, indirect costs, and intangible consequences. And the direct damages are the things like the structure gets damaged, a roof blows off. They're the things that people tend to think of first when they think of hurricane damage. And they're fairly easy to quantify in dollar terms. The indirect costs are the lost wages, the business interruptions, the cost to clean up after some event happens. This morning, somebody was telling me that there was sand on rooftops, and that cost money. After this past hurricane went by, and that cost money to clean up. So there's an indirect cost. And then finally is the intangible consequences, and these are things that are very difficult to put into dollar terms. There are things like environmental pollution from oil spills after a petroleum tank gets damaged in a storm, or the impact on quality of life. So this is from a newspaper article after Katrina. This was 8 months after Katrina. This article came out, and the headline is "Rotten Meat from Katrina Still in Gulfport Neighborhood." So in this particular example, this warehouse, this was a refrigerator warehouse in Gulfport that stored chicken and pork bellies. Storm went by, blew out the whole bottom of the warehouse. The surge went 3 miles inland into the city of Gulfport, carrying with it bags of chicken and pork belly. They landed in people's yards all over the city, and they basically sat there and rotted. And there were, the question of who is responsible for going around and cleaning up all of this mess went unanswered for at least 8 months, because 8 months later people were still complaining about it. So they're complex issues. Climate change, of course, exasperates all of this. And for ports and for port cities, typically the three main climate change drivers of concern are the projections for a doubling of Cat 4 and Cat 5 tropical storms by the end of the century, sea level rise, of course, and the consensus right now is that the range by 2100 is somewhere between 3/4 of a meter and 2 meters, although the most recent NOAA projections are quite a bit higher than this for the extreme scenarios. And then finally, the inland flooding event that comes with extreme precipitation. And so if we take these three drivers and we bundle them together, like some researchers have done for some areas of the North Atlantic, they found that what is today the 1% annual flooding event, annual probability flooding event, the 1 in 100-year event, with those factors combined, could become the 1 in 3-year storm event by the end of the century. So big changes in our coastal environment. So this leaves our planners and our decision makers and our policy makers in somewhat of with a conundrum, which in the academic world is sometimes called a wicked problem. These are very complex problems, no easy solutions, winners and losers always with any solution that you might propose. And they're the kind of problems that often result in people just kind of putting their head in the sand and hoping it'll just go away. So for the climate change issue for the coast, these problems are a result of things like uncertain rates of change. So we've got a range of sea level possibilities to deal with. And constructing something for a 3/4 of a meter of rise is very different than constructing something for a 6-meter rise. So where do you fall on that? Feedback loops, which are still being being studied and not always well understood. Misaligned incentives, so for example, the National Flood Insurance Program, there's a misaligned incentive where people are being subsidized to rebuild on the coast. Where's the money going to come from? There's big projects are going to be necessary for our coasts, and it's not clear where that money will come from. And then the adaptation options are often very confusing. So that leaves us with this predicament. What do we do? And we heard it this morning at the Tower Forum. People want answers to this problem. They want to know. Just tell me what to do. And unfortunately, it's not that straightforward. So what I propose is that we, as a society, we need a fundamental shift in how we think about the future. When we look at our timeline here out to 2150, here's the magic 2100 number that we expect all of these things to happen by. But of course, we know that they will continue to happen beyond 2100. And in fact, the rate of rise will only be increasing over time for sea levels. The intensification of these hurricanes will also likely be increasing over time. So it really doesn't matter if we're talking about 2100 or 2150. These things are coming our way. So we're, as sort of a species, we're pretty good at thinking about the present. We can think about our one-year plans for our businesses or our communities or our election cycles. 5 to 10 years out gets a little bit fuzzier, but we can still have a pretty good plan or strategy for what we want to do in the next 5 to 10 years, whether we're talking about our own lives. These students who come into to our schools, they know that they're going to be here for 4 or 5 years, and then they hope they're going to get a job at the other end. So that's a time scale that we're used to dealing with. After that, the things that we might think about are our career spans. So, for me, I think I've got maybe another 35 years of research ahead of me, I hope. And then things start to get pretty vague and fuzzy after that. Who thinks about the rest of their life? Probably not too many until maybe you've reached towards the end, and then it's a much smaller time scale, so you can think about it then. But next up is thinking about the lives of our children, so the next generation. There was a paper that came out that was saying that children born in the U.S. today, more than 50% of them will live to be 105. So lifespans are increasing. It's not to say they'll all live to 105, but 105, that gets us well out past this 2100 mark. And then after that, it's like, maybe our grandkids' lives, and then we're really getting out into the 2150s. So, we have to start thinking about this time span, and we have to start thinking about it now. And the reason is that we're going to need to implement major infrastructure projects like the Maasvlakte barrier here in Rotterdam, in the Netherlands, which was inspired by the 1953 floods in the Netherlands and was finished in the late 80s or early 90s. And these projects take a long time. They can take 5 years or so to engineer and design, let alone picking the project that you actually want to do, which will likely be very contentious when we're talking about infrastructure projects on this scale. They can take 10 years to get through permitting and regulations and the regulatory process. Maybe another 10 years to construct, if you're lucky, not quite that long, but it could take 10 years. And then they typically, because they're infrastructure, they've got a design life of around 50 years. But if you go down to any coastal city or port in the world, you will very likely find infrastructure that was built well over 100 years ago that's still up and functioning. So the actual working life, even though we're only designing them to last 50 years, can be more than 75 years or even 100. So the decision process is starting over here, where we're good at thinking about the present, but the implications are way out here, and we just don't really have, we're just not programmed to think on that kind of time scale. So how do we get there? So the research that I'm doing with my group at URI is trying to address this big picture question of how can a more holistic approach to planning reduce climate risks in the environmental, social, economic, and political landscapes. And that's a big, broad question. That's my 35-year career question right there, plus the question that I hope some of my students will go on in their careers to help answer. But I'm going to give you 3 examples of research projects that begin to contribute to an answer to that question. So the first one is about deepening our understanding of this concept of vulnerability, looking at ports as a case study for that. The second is looking at some ways to better communicate risk. And the last one is an example of how we've used some of these tools to engage stakeholders, especially private sector and industry stakeholders. So I'll go through each of these pretty quickly, and then we can have some discussion. So this first project is deepening our understanding of vulnerability. So we have some fairly good methods already for doing what are called vulnerability assessments. They're typically done on a single case scale. So I'm interested in ports. There's some good methods out there for conducting a vulnerability assessment of a port. You get your local experts together, you maybe bring in some outside experts, you can go through a process of looking at the different pieces of infrastructure you have and different projections for climate, and write up a report that identifies the areas that need to be concerned about. So that's great, and that's happening in different ports and in airports and in power plants and in communities. But what we have less understanding of is how to think about relative vulnerability. So, from a federal agency perspective, there's going to be an awful lot of money that needs to be spent on enhancing resilience, whether it be in communities or airports or power plants or wastewater treatment plants. A lot of that's going to be federal money. And there needs to be some methods for doing some prioritization, and as one of the discussion points in making these decisions. So how do we understand which ports are more vulnerable in what ways than other ports? Is the Port of New York more vulnerable than Boston or less? So these are fuzzy concepts. They're not directly measurable. So we need proxies. We need indicators to help us understand these concepts of vulnerability. So in the academic literature, vulnerability breaks down into these 3 big buckets. Vulnerability is a product of these 3: exposure, sensitivity, and adaptive capacity. So we're looking for indicators of these concepts on these 23 ports in the Army Corps of Engineers North Atlantic District. So these are the medium and high use ports. This is work being funded by the Corps, by the way. So our first task was to really kind of define what do we mean by vulnerability and what do we mean by these 3 terms. So I'll go through them quickly. Exposure, and you may be familiar with these already, but exposure is this concept of where you are with respect to the event of concern. So the presence of people, livelihoods, et cetera, in settings that could be adversely affected. So these are our ports that are in the hurricane belt. The blue ones are the ports that are not in the hurricane belt. So you could say that the green ports have a higher level of exposure to hurricanes than the blue ports. So you could have an identical set of infrastructure, and if you're located on the eastern seaboard, you're exposed. If you're located on the west coast, you are not exposed to hurricanes. Sensitivity is how much your object of concern or your system of concern will be affected by a given event. So here we have 2 examples of warehouses. This is a wooden warehouse, happens to be in Brussels. This is a concrete warehouse in Los Angeles. If you put these 2 warehouses on neighboring parcels, no matter where they were with respect to hurricanes, this one would be more sensitive than this one. Okay, so the exposure could be identical for the 2, but the sensitivity is much higher for the structure that's not built as well. And then finally, adaptive capacity This is sort of the resources that you have to bring to bear on making your system more resilient. So in the case of ports, low adaptive capacity would be a port that had no master plan, no redundancy in their systems. Maybe they only have one power supply. They have no generator, no backup generators. They don't have any funding to put into building resilience, whereas a high adaptive capacity would have maybe a port resilience officer who's a line item staff position in their budget who's solely dedicated to trying to make their port more resilient. So that's the adaptive capacity piece. So we identified these components, and then we searched for publicly available data sources that could provide proxy indicators for these different components. So we went out and looked across all of our agency data sources and what was available through web searches, and we identified a whole bunch of data sets, and within those data sets we found 108 candidate indicators for these different concepts. And then we did we worked on with an expert group of port resilience experts that started with the Resilience Interagency Task Force, which the Army Corps and NOAA and DHS and others are part of. And we snowball sampled with them until we got a group of, I can't remember the exact number, I think it was around 65 port experts to help us narrow down these 108 down to 34. And then we worked with the same expert group in a mind mapping exercise and kind of dug into those indicators in more detail, and we settled on 12. And then we used an analytic hierarchy process to develop some rankings for how well these different indicators correlated to the concepts, and then how well these experts felt that those indicators represented those concepts. And so this work is unfinished. We have our indicators selected. We've been through the analytic hierarchy process, and we're in the data analysis phase of that. So where we're hoping to go with this is to develop something of a scorecard, and we're being sensitive to the idea that scores can be dangerous. So we're not, because there's winners and losers, right? So if you're a port and you see that you have a great vulnerability score and you're not very vulnerable, well, that's terrific, but you may be ineligible for certain funding that might come down the line because you're showing up as already resilient. And vice versa. You may not want to have your port show up with a score that says you're very vulnerable because it may be harder to draw customers in, for example. But we do want to be able to at least develop some scores for these components of vulnerability. So these are just some examples. This is a mock-up, but these are the types of indicators that we're looking at. The number of storm events, the number of endangered species in the area, the number of vessel calls, the export tonnage, the number of air pollution days, et cetera. So we can come back to that at the end. I just wanted to give an overview of that project and then move on to the next one. So the preliminary findings are that there are good indicators, especially for exposure. And in fact, there have been studies on coastal city exposure only globally. Using similar indicators. There's good indicators for sensitivity, but adaptive capacity, our experts looked at our 108 indicators and said none of them correlate to adaptive capacity. So there really is no good data out there to serve as a proxy for understanding adaptive capacity. And there were a number of data sets that we would love to have to add to this, but just simply don't exist. Okay, so second project. So we're moving from understanding vulnerability now to communicating risk and thinking about ways to communicate risk. So we've been developing what we call a virtual disaster impacts model. So what this is it's an integrated approach that starts from hydrodynamic ocean models. So we work with the Graduate School of Oceanography at URI. And we take the outputs from their very high resolution hurricane models, which give outputs including expected wind, expected surge for different areas, velocity, and wave heights. So we take those model outputs and we bring them together with a number of other models. So it could be things like damage functions that might come from the Corps of Engineers for structures. So for example, if you have I'll show you some examples of this, but if you have a wooden structure and there's 5 feet of flooding, you might expect 50% damage. And the Army Corps has these damage curves. We can bring in economic models that would say with this amount of flooding for an area, you would expect so much economic impact. There's a lot of assumptions built in, but we're not making those economic models. We're using them. We're combining them with these other models. Or, as in the case in a project we're working on in Rhode Island right now, we're actually interviewing facility managers of critical infrastructure facilities. So, for example, wastewater treatment facilities, and asking them to put in the terms of the model parameters what their concerns are. So if they're concerned with a settling tank being inundated, we're asking them to put that in the terms of the model. So how much flooding is going to cause that inundation? If they're concerned with a road being shut down, an access road being shut down, we would ask them, well, what are the things that we can model that would cause that road to be shut down? Is it a flooding event? Is it a wind event? Is it a bridge that shuts down when the winds get to 65 miles an hour? So we using expert elicitation, we bring those into the terms of the model, the hurricane models. And then using some 3D visualizations, we can output products that are more tailored to different audiences. So I'll show you just a couple of preliminary examples of this. This is an integrated disaster model that includes the hurricane model, a sea level rise model, and the damage functions from the Army Corps, plus a data set of building footprints that came from this town. This is the town of Matunic in Rhode Island. The top is to the north. The bottom is the Atlantic Ocean. And so what this is representing is the community in Matunic with each individual house modeled as its own 3D model. So this is not one rendering. This consists of individual 3D models for each little structure that you see here. And that means that we can represent each of these 3D structures differently depending on what the inputs to the model are. So for example, here we're looking at the 1 in 100 year storm event with no sea level rise, and the damage function is represented by the yellow to orange bar here. So 100% damage is in the red. Green means not damaged at all. And if you look at the coastline here, we can see there's quite a few structures that are not damaged at all. But when we run the same hydrodynamic storm model and we add in the sea level rise to it, here's what happens. Here's one more, just another view of the same thing. So now Atlantic Ocean is to the right, north is to the left, and this is the 0 feet of sea level rise, and here's the 7 feet of sea level rise. And so this is based on knowing what every structure is. So we get that from the town planner. They've got a database of all of these different structures. We know if it's a 1-story or a 2-story or a wooden structure or a cement structure. And then those damage functions from the Army Corps. So this is the first iteration of this kind of a visualization. But because each of these structures is its own 3D model, and we've built custom ones for certain buildings. So like, so there's most of these are generic, right? But this is a building. You can see it's different from all of the others. So we built this one custom because it's a recognizable building that people are familiar with in this neighborhood. This is the Ocean Mist Bar. Everybody knows it. Everybody goes there. It's a well-loved spot. But where we don't have to build custom models for every structure, we don't. We just use a generic model, which just sort of depends on the scale that you're going after. So this is a first iteration of this integrated modeling approach. And one of many directions that we would like to go in with this is to represent this damage in a way that's even more meaningful to the viewer. So rather than do a red box, because for each model we know this is a 2-story building, we know it's made of wood, we know it has an asphalt roof, and we know, a few other things about it, we can represent that using a texture or a skin on that model. So instead of just coloring it red, we can do something like this. So same 3D model, but instead of a red box, we're zooming in, and we can use the shingle texture and the asphalt roof texture and some damages. So if it's a 30% damage, we can represent it with broken windows. If it's a 8-foot storm surge or whatever this foot is, we can represent it with a mud line at 8 feet. If we run a different storm model, or we don't want to have as much sea level rise, the visualization would show up with that mud line lower down on the house. So, and each of these pieces of debris in this model are also a 3D model. So that means that each piece of debris, and they're generic. I mean, these are, there's like 5 different types here, but they represent debris. Each one can have its own parameters. It can have buoyancy, it can have size, it can have volume, which means that we know what its properties are, and we can integrate yet another model, like a particle model, and we can show how that debris might move if we know the velocity of the currents there. And so our visualization can show if the water's all pushing this way, that debris can move with that visualization. So this is one of the places that we're going with this. I'm just going to show you a few more examples of the kinds of things that can come out of this. Again, this is a fish barrel. This is Point Judith, Rhode Island. It's a fishing port. So lots of fish barrels that ended up as debris. And we can do other kinds of infrastructure. These are custom-built ones as opposed to our generics. Okay, so what do we do with this? So the tool, it's a tool, it's a communication tool. There's all sorts of applications for it, including with the insurance agencies. What we've done is an emergency management agency exercise hurricane scenario exercise in Rhode Island. So it was a 5-day scenario planning exercise that had all of the different state agencies come to kind of walk through a hurricane scenario. They all had stations, and some of you have probably seen these things. They all have computers, and people feed from another room. They feed in, okay, there's somebody trapped on a roof, and then that triggers somebody saying, all right, well, we have to send some rescuers over, and they kind of do this simulated exercise. So they used some of our models in that exercise, and we created these what are called injects, which is it's the event that the participants are told happens that they have to respond to in the scenario. And we didn't go quite this far with it, but this is kind of the next step, how we could use these in a hurricane scenario exercise. So what we're looking at here is the Port of Providence. North is to the right, so up this way. This is a simulation of Hurricane Carol, which was the last major hurricane in the Port of Providence, 1954. But it's overlaid on today's infrastructure. And in this mock-up, we've interviewed the facility owners of the different infrastructure facilities around the port, asked them what their thresholds are for different levels of flooding. And in this case, we're looking at a petroleum company, not its real name, petroleum company there. This is what's in it. It's a Class 3 liquid bulk storage facility, and what the facility manager told us ahead of time, before the simulation, we went out and did these interviews, is that, well, when there's about 1.5 meters of flooding, we would expect our containment berm to be flooded. What does that mean? Well, it means that the pipelines might be damaged, and it means that responder access is going to be obstructed. So when we run the storm model in time, once this flooding from this Hurricane Carol event hits 1.5 meters, it pops up. This is an area of concern, and these are the things. Yes, the concern is that the containment berm is flooded, but who cares? Well, who cares is that the pipelines are going to be damaged and the responder access is going to be. So this is an example of how we can use these kinds of tools. But one of the important questions with these visualizations is, are they doing what we want them to do and what we think they're going to do? So we make these kinds of visualizations, whether it's these 3D ones or whether it's NOAA making their flood mapper. And as creators and scientists who are putting these visualizations of flooding together, we have some intent. We're trying to represent some level of risk or some level of flooding, whether we're conscious of that or not. And so one of the important questions is, what are people coming away with when they see these visualizations? We've got a whole bunch of experts doing different things to make one of these happen. But when the public looks at it, is the level of risk that they're perceiving from that consistent with what we hoped it would be? So we're doing a big social science methods survey of the public to look at a couple of different kinds of visualizations and see how their familiarity with the location will influence their perception of risk, their perception of who made the visualization, will that impact the credibility of the images, and how well does the perceived risk align between the public who's looking at it and then the experts who actually put them together. So that's another project that my student's working on. Okay, so then the last project, so we've looked at deepening understanding of vulnerability. We've looked at how to communicate risk, and then this last project is how do you engage stakeholders who maybe don't really want to think about this stuff. So we with Department of Transportation funding, we ran a workshop in the Port of Providence, and we worked with all of the business managers and owners in the port. There were about 30 of them, to facilitate some dialogue around what would a major storm mean, not what does the event mean, because people do tend to think about that. They've got hurricane response plans and evacuation plans. So they do a pretty good job. But what does it mean in the weeks, months, and years after the event? So what does recovery look like? Affect your business, not just on that day, but in the longer term. And then can we get people to think a little bit more about these long-term solutions, like that hurricane barrier, the Maslach carrying barrier that took 50 plus years to actually get implemented? Can we start thinking about that now? And how well do different long-term strategies meet the goals of stakeholders of a place like this? So this is our study area in Providence. This is the port proper down here. But this is an energy port, so it supplies all of the petroleum product for the whole state, plus parts of Massachusetts and Connecticut, including our airport, TF Green. But there's a few other types of businesses in here too. And we spent about a year with a steering committee putting together this workshop methodology. Okay. So here's a couple examples of what the port looks like. This is from the last major hurricane, which was 54, and before that was 38. Most people don't remember these. So how do we get them to think about these things? So we held this workshop with these stakeholders, and we looked at 3 tools. The first was a storm scenario. This was before we were doing all these 3D visualizations. So this is an extreme but plausible Cat 3 event. It generates about a 21-foot storm surge for Providence Harbor. And we created visualizations just using Google Earth of every property that was represented by stakeholders at our workshop. So everybody got to see what their particular spot would look like, as well as their neighbors in this flooding event. So the normal coastline runs down about here. So this is a pretty severe event. These are all petroleum tanks. And through breakout discussions, we kind of brainstormed what the major impacts would be over the long term. And then using that as a base for discussion, we introduced 3 archetypal long-term resilience strategies. So they're accommodate the flood, or protect your area so it doesn't get flooded, or relocate outside the area. And we these concepts with some of the pros and cons, We didn't generate costs, but we talked about what the types of costs and benefits they might expect. So accommodate might be elevating the whole land area up to get it out of the floodplain or doing these site-specific improvements. Relocate would be moving port uses out of the port, really, out of the floodplain. So, and we had an example of that right in our study area. This is an ExxonMobil terminal, and up here, there's a tank farm, and it's elevated to 50 feet. And this was not done for flood protection, but it's the kind of thing you could do to get those tanks that you saw flooded in the last picture out of the floodplain. And then finally, we built the Maslach carrying barrier for the Port of Providence down here in our landscape architecture studio, and a berm to go with it, and a bunch of other things, and looked at that as a storm protective measure, which would prevent storm surge in the whole port area. So we took those concepts of protect, relocate, accommodate, and then the do nothing concept, that's the current plan. And we asked the stakeholders to come up with 7 resilience goals. So each of these colored bars represents one of their resilience goals. So ensure business continuity, foster port growth, protect human safety and critical lifelines. And we asked them through a tool called WeCision, which is an online, in real-time tool. They can sit there with their computers and enter their answers. How well do they think each of these strategies would meet each of their goals? The thing tallies it up in real time. They can see the results right there. And what we found in this exercise was this particular group of stakeholders felt that building that barrier would best accomplish their goals. So it kind of shows up as a favorite, but it actually isn't necessarily a favorite. It just means that it does the best job for those particular goals. And despite relocate coming in second here, they hated that idea. They didn't want, we don't want to talk about relocate. It's a common theme. We talked about not talking about it this morning. Okay, so the findings from this, we found that although there are hurricane response plans, there's no long-term plan for hurricanes. These folks, it was hard to get them in the room for half a day. This is something that will affect them for sure when this storm happens, but it's just not a priority for them to think about something to do with their Wednesday afternoon. Leadership was a big problem. There's no clear champion for this problem in many places, including the Port of Providence. And people want to know how much it's going to cost. And unfortunately, figuring out how much it's going to cost it's going to cost a lot just to figure out how much it's going to cost. So we didn't have good answers for that. But we do see that the results of this are making their way through the system in the state of Rhode Island, and people refer back to these ideas, and now there is some momentum around conducting a new barrier study to see how effective the existing barrier is, and should we build a new one, and should it be in the other place. And I think that came from this workshop in part. So to wrap up here, so I've talked about deepening understanding, how we communicate risk, how we can engage people who don't want to talk about these things in these conversations, which hopefully help us to answer this big question. And I will leave with this kind of concluding thought that leadership is a really important piece of this puzzle, and it's not showing up in at least in the work that I do. There is leadership on some scales, but certainly for the maritime port sector, there's not a lot of leadership for building long-term resilience. And I think part of that is due to a lack of incentives. So, and what I've thought about a lot is the fact that the universities are the places where the incentives actually work. So for a private business to think about what's going to happen in 50, 75 years, that's not really in their wheelhouse. On the political front, our political leaders are thinking about election cycles and what's going to get them elected, and they're trying to keep the schools running and the streets clean and and all of those things. So thinking about resilience by 2100, that's not going to end up at the top. But for the university, we're here to think about these kinds of problems. Our incentives are publications and grants. So we can certainly publish on this stuff and get grants to support it. So I think partnering with the universities, like we saw this morning, at the forum is a really important piece of this, and getting that linkage between the business sector, the public sector, and the universities is critical. So lots of people involved with these projects, and that's the end.